quality of satellite communication signals related to problems in RF block. There are many components and elements that are included in the a wireless communication systems, but I had to focus on the critically important roles of radio frequency passive components, such as antennas and microwave and millimeter wave components, especially feeding structures. As you see, the beam that is steerable by the array antenna, I have designed with my students and research associates, and this is an example of far field that is steerable, and this one is the actually the all these are animated versions. Yeah, as you see here, animated versions. Yeah, it is moved and tilted from left to right, and according to the scenarios you can set up, and according to your customers' voices, you can adjust the beam trajectory of the beam from left to right or from north to south, whatever. And on your right-hand side, the electric field distribution that is moving and actively working when all the patch elements of a beam-forming antenna are cooperatively to create a certain angle of beam. So dependent upon the feeding structures and the aims and objectives you set according to the requirements, the field distribution might be different from what you see now. And today I would like to especially emphasize the importance of the advantages and sophisticated roles and functions of passive components, even though there are other important parts, including digital and active, but passive components, without pumping the DC power there, it changes the level of well, it changes the properties of frequency. It is not like a modulation or demodulation, but if you accept several different frequencies, but your triplexer or multiplexer can distinguish one frequency from the others like that. Very important function that should go through when you deal with the system development for wireless communication. Motivation, representative components in RF block for satellite communication. Highly likely problems and ripple effects will be highlighted there. And finally, I will conclude the content of my talk. And as one of my research associates has shown the light on the importance of the beam alignment between the transmitting antenna and the receiving antenna, though for the sake of convenience, we changed the angle of beam from the source antenna, horn antenna, mechanically, but receiving antenna should change the beam of radiation at a certain angle electronically. So using the switch, you can choose the one out of the input ports, then you can steer the beam. Then you can expect misalignment or alignment between beam from the TX or transmitter and beam from the receiver, like that. When you have good match between the angles of the beams meet together from the transmitting and the receiving side. As you see, the 64 constellation pictures show you the clearest. This is the best quality. That means the beams are well aligned, but these beams are just fixed, just forefront of the aperture of the horn antenna and the aperture of this planar structure. but if you change the position and orientation of the horn antenna mechanically, the receiving antenna should be smart enough to track the beam from the transmitting antenna. So except this, this antenna, it was moved from the central location of on the bar on the right hand side. Actually, it doesn't have the function of beam forming or beam steering. Then this sees this direction. The beam from the receiving antenna sees minus z direction, but the direction of the horn antenna sees, say for example, 45 degrees from the horizontal axis. Then we judge that's the misalignment between the two beams. Then inevitably, electromagnetically transfer efficiency between these two antennas goes down very drastically. That results in the blurry picture in the constellation. This is the worst case. So we would like to get out of this situation by giving the function of beam steering to this antenna. So there, wherever your receiving antenna is located, as far as it has the function to steer its beam, then alignment between the beams from the TX and RX sides is realized. Then, as you see here, these four constellation pictures show you good quality in communication. So I would like to put the stress on the linkage between the electromagnetic thing or RF thing heavily related to the final quality of the communication system. And we did the similar approach to see the characteristics of communication, quality of the communication on the basis of the RF components. So here we have good multiplexer here. The transmitting antenna has a wideband for signal sending, but we would like to distinguish the one channel from other channels. So here, when the channels are selected, even with this passive component named multiplexer, everything is what this is a passive component. Well, these days, what about regarding RIS? Most institutes say their antennas or reflective reconfigurable intelligent surfaces are purely passive, but they are lying. Actually, they are wrong. The reason is they at least use bias circuits there. Bias circuits need DC power. Then that means that is an active component. But all these what wanted, desirable things are happening by using this passive components. It is easy and low power consumption, almost zero power consumption, and metal surface, which paves the way to make a reconfigurable intelligent surface. From state to state, we can design the RIS or metal surfaces to have different angles of reflection. The angles of reflection can differ from the angle of incidence. They are different, but in basic electromagnetics or other practices, even done by big conglomerates, what they do is very lukewarm approaches, but we don't follow their ways. So as you see, we developed the sensor and probe to test the detection of the electromagnetic wave of power reflected by this bizarre surface. But now the name has been settled down, that is metal surface, which is the building block for the RIS or IRS. And RIS, that is based on metal surface, which comes from people's desire to change the curved structure to a planar structure while it maintains the same function. So we did as my research assistant showed the results and as well as the design procedures, we could develop them like these. We can steer the beam angle of reflection like this by changing the surfaces. But all these are passive states. And yeah, apart from that, we see a series of system block diagrams for transponders of satellites, even though they started to talk about LEOs, but they do not. Mostly they barely have the experiences of developing the real satellite transponders, but I'm exceptional. I developed 2 models of satellites before, especially transponders. By the way, these pictures are quite familiar to me, and even system block diagrams of the transponders for a satellite, they look almost the same as the system block diagram of a mobile communication system. But here I highlighted the positions of the passive components, which select the frequencies and channels and suppress the noise, which is unwanted to the input of the active components, such as amplifiers. So there are a lot of work that should be done while others pursue the development of passive active components or beamformer chipset. But I'm really kicking out of the fields of the passive components. You can see the positions of the filters and the multiplexers, input multiplexer and output multiplexer. And recently, my students could develop the idea how to design the multi-beam array antennas like this. That's very interesting. And even before, many people show the results or just papers regarding filtered antenna or filtenna. But my work dates back almost more than 15 years ago. That's when I started. But this one, when the popularity on CubeSats or minisats was rising, I jumped to that field, how I can handle the change of the classic antennas to the modern new antennas for the purpose of saving the cost and saving the volume, physical volume, because the satellites are flying over us. That should be as light as possible. To do that, we try to cut down on the cost to develop the things and maintain them, the satellites. But this is seriously treated in the field of LEO these days. And my students have designed and developed the very handy and light filter, extended filter structure like the duplexer here, very compact compared to the classic waveguide structure. We can deal with the design of duplexer for in the frame of a waveguide, but here spurious problem occurs, then other techniques should be applied there to suppress this field. But as far as we have zeroth order resonators for X and Q band in the form of duplexer, we do not have spurious. As you see here, if you want to handle an X band and a KU band, because of the spurious, actually the passage of the KU band signal is much deteriorated by the spurious component. How can we put down the level of spurious component? We just use our own zeroth order resonators for these 2 different frequencies together in one structure. Then we can handle the spurious and a very much desired result like this in terms of S21 and S31. And also we have developed the 3-dimensional sorry, 3D printed filter working with the AGG and LIG next one. Yeah, they are really appreciating us for developing the new structures for them. And also we tackle the problems of the slot array antenna, which should be very light and compact. This is one of the prototypes we have designed recently. And using, based on this structure, you can steer the beam almost everywhere, the full coverage of the hemisphere from you to the sky. And almost, we are approaching the end of the talk almost. As you know, the bandpass filter like this, and following the conventional bandpass filter design, this is at this size is what we expect easily, but we could diminish the overall size like this. Almost half of the classic structure or conventional structure. And this is the picture of we recently developed, very small, so very light. So they have no choice but to use our passive components for developing the light satellites, such as LEO satellites. And we got good bandpass filter performances like this for low frequency, for high frequency. These two frequencies go together, and please be mindful. These two frequencies are quite adjacent. Actually, just it is contiguous channels, but others use put the gap between the two as adjacent frequencies. But for us, actually, we handle the the hardest problems in the filter design. As you see here, skirts, the roll-offs are very sharp here. So the interference between these two bands are as low as possible. And we went further. If we have a good passband or BPF for F1 and BPF or bandpass filter for F2, when these bandpass filters are combined with the horn antenna for feeding, like this, signal for F1 is well accepted, while signal at F2 is not accepted. That's what the bandpass filter of F1 is expected to do. And this also applies to channel F2. F1 frequency is not accepted by the bandpass filter for F2. These are the results of the bandpass filter combined with the horn antenna for high power transmission. So, the last but not least, I'm telling you, if you cause a little, tiny little possibility of failure, of mechanical failure, compared to this, there are two irises that are distorted. This is the regular and healthy one, but if this is an unhealthy one, in the passband, the horn antenna beam patterns which were healthy can get ill like this. The beam of as you take note of the level of the antenna gain there, very small because of this distortion, mechanical distortion. Mechanical distortion is related to the RF function, and RF function finally leads to the success or failure in communication system. That's my message today. So I would like to wrap my talk up by saying we cannot separate the topic of radio frequency and passive component and antenna fields from communication system development. That's my message. Thank you. 자, 긴 시간 얘기는 했지만 여러분들 우리 라디오 프리퀀시 특히 이 밀리미터파든 마이크로파, 저주파도 하지만 저희 연구실이요. 그쪽 분야에서 이제 연구되고 있는 분야는 언제나 쓰인다는 거. 그리고 감초 같은 역할을 한다는 거. 우리 방 이제 연구원들뿐만 아니고 수동소자나 안테나 하는 사람들 제대로 하면은 이제 제대로 인정받는다는 걸 알아주시기 바라겠습니다. 그래서 위성에 관련된 얘기는 제가 이제 발표하면서 이제 했고요. 그 외에 이제 전자파 분야, 뭐 전자파 분야는 전자파 학회 가실 필요 없이 저희가 다 커버할 수 있을 정도로 다 하니까 뭐 그네들부터 많이 더 멀리 더 높이 하고 있으니까 여기 와서 많이 들으시기 바랍니다. 그럼 여기서 제 발표는 마치기 바라겠습니다. 자, 혹시 질문이 있는지 제가 잠깐 볼게요.